Welcome to MRS Bulletin's Materials News Podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Sophia Chen. Right now, materials scientists are excited about a category of materials known as colloidal materials. These are liquids with nanoparticles suspended in them, and they're exciting because they're so versatile. By changing the size, shape, and chemistry of the nanoparticles in the liquid, scientists can tailor the properties of colloidal materials for specific applications, from sunscreens to thin films on solar panels to 3D printer ink. Chemist Xingchen Ye of Indiana University studies the fundamental behavior of colloidal materials, which allows the field to better design the materials for desired applications.
We are developing new types of colloidal materials that has emerging physical and chemical properties.
In particular, Ye's team is interested in how a colloidal material's properties change as you spatially rearrange the nanoparticles in the liquid. For example, they studied cube-shaped gold nanoparticles dissolved in a solvent. The gold nanocubes can interact to form collective objects known as plasmons. Whether the plasmons form depends on how the gold nanocubes are arranged in the solvent. Researchers are interested in materials with plasmons for applications such as solar panels because the plasmons make the materials scatter or absorb light at well-defined wavelengths. Ye's team designs the materials such that the nanoparticles arrange themselves in a process called self-assembly. After the gold nanocubes self-assemble into a lattice structure, Ye's team studies how that structure gives rise to the material's bulk properties. But researchers still lack fundamental understanding on how to control the self-assembly process to get the nanoparticles to form the desired structures.
If you are given a certain nanoscale building block, such as spheres, cubes, or other shapes, and a given assembly condition, how do they assemble into their thermodynamically favored or even metastable structure? How do they get there? How do you probe that process? How do you understand that process?
To better understand the process, Ye's team studied self-assembling gold nanocubes dissolved in various solvents. They were able to make the nanocubes arrange themselves in simple 2D lattices, such as squares, rhombuses, and hexagons, on the order of tens of seconds. They imaged the self-assembly process in real time using a transmission electron microscope. They could control what structures the nanocubes would self-assemble into by tuning the polarity of the solvent where the nanocubes resided. They tuned the solvent's polarity by mixing butanol, which is the more polar solvent, and octane, which was the less polar solvent, in different ratios.
We can access any polarity in between by mixing the two in different proportions.
Ye's team also worked to develop a mathematical theory about the self-assembly process, which they used in simulations. The theory and simulations allowed them to predict, given certain solvent conditions, what final structure the nanocubes would assume. It also let them predict the process by which the nanocubes go from being dispersed in the solvent into a densely packed array.
The challenge we are trying to address is really the lack of understanding of how does the interactions between individual particles influence or even dictate the self-assembly pathway. It's not just the destination, it's more about the journey.
This work was published in a recent issue of Nature Chemical Engineering. My name is Sophia Chen from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org and follow us on X at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.